Okay, just take a quick look around you. The phone in your hand, the car you drive, the very wires inside your walls. They're all made of metal, right? We use this stuff every day, we totally take it for granted. But have you ever really stopped to think about what makes a metal, well, metal? Why can we bend the paperclip but not a piece of charcoal? Today, we're diving deep into their secret superpower, right down to the atomic level. So check this out. On one side, you've got something like copper. It's shiny, you can bend it into all sorts of shapes, and it's an amazing conductor. Then on the other side, you've got sulfur. It's dull, and if you even try to bend it, it just crumbles into dust. What is the fundamental secret that puts these two on completely different teams?
To figure that out, let's start with the obvious stuff. The great divide that we can all see and feel with our own hands.
This table really just lays it all out, doesn't it? Metals have that classic shiny luster. Non-metals, they're usually pretty dull. Metals are what we call malleable and ductile, meaning you can hammer them into thin sheets or stretch them into long wires. Try that with a non-metal. Yeah, not gonna happen. It'll just shatter. And of course, the big one, metals are fantastic conductors of heat and electricity. Non-metals are the exact opposite. It's like they're from two different worlds.
But here's the thing, all those differences we just talked about, they're just the symptoms. The real cause, the actual secret, it isn't something you can see. It's all happening at a level that's completely invisible.
The entire story, and I mean all of it, begins at the atomic level. It all comes down to the electrons in the outermost shell, what we call the valence electrons. A metal like sodium, on the left, has just one lonely electron that it is more than happy to give away. But a nonmetal like chlorine on the right, it's desperately holding on to its 7. And believe it or not, that tiny little difference explains absolutely everything.
So, let's get to the big reveal. Let's see how that one little detail builds into something totally unique, the secret metallic bond.
So here's the formal textbook definition for you. A metallic bond is the force of attraction between positive metal ions and the cloud of negative electrons that surrounds them. Okay, simple enough. But what does that actually look like? What's going on in there? Well, it all happens in two main steps. First, metal atoms don't just float around randomly. No, they line up in this super organized, repeating pattern, kind of like a 3D grid. We call this a crystal lattice. Think of it like a perfectly stacked set of oranges at the grocery store. And now for the magic trick. Once they're all locked into that neat grid, the atoms let go of their outer electrons. These electrons are now free. They don't belong to any single atom anymore. Instead, they form this free-flowing, shared sea of electrons that swarms around all the positive metal ions. This mobile sea of electrons, that is the superpower. It's the reason metals are shiny, conductive, and bendy. It's the whole secret.
Okay, so that's a really cool theory, right? But is there any proof? Well, let's take a look. And the proof is actually based on a really simple idea. More electrons equals more strength. The logic here is just so elegant. The more valence electrons an atom tosses into that sea, the stronger the electrical glue holding everything together becomes. The metallic bond gets stronger. And a stronger bond means the metal's going to be harder, and it's going to take a lot more energy, a lot more heat, to break those bonds and melt it.
And this chart just shows it perfectly. Look at sodium on the left. It donates 1 electron, and its melting point is a measly 98 degrees Celsius. Next up, magnesium donates 2 electrons, and bam, the melting point jumps all the way to 650 degrees. Then you've got aluminum, which donates 3, and its melting point is even higher. You see the pattern? More electrons, a stronger bond, a higher melting point. The connection is undeniable.
All right, so we get the science. But why does this actually matter in our everyday lives? Let's talk about the payoff. How we can remix and reuse metals, all thanks to this special bond.
You know, a lot of pure metals are actually pretty soft. So for thousands of years, we humans have been acting like elemental chefs, creating what are called alloys. An alloy is really just a custom mixture of melted down metals.
A classic recipe is bronze. It's mostly copper, but you mix in just a little bit of tin, only about 5%, but that tiny addition makes a world of difference. The final alloy is way harder than pure copper, and it's also great at resisting rust. You're basically taking the best properties of each to cook up something even better. And we see the results of this genius idea everywhere, from the medals hanging around champions' necks to incredible statues that have been standing for centuries, like the famous lion statue of Qasr el-Nil. That's the power of learning how to manipulate these metallic bonds.
This all leads us to a final, and honestly, a super important question. If you think about that sea of electrons and how metals work, Why is it so incredibly vital that we recycle metals like aluminum?
There are a few massive reasons. First, these metals are a finite resource. They don't last forever, and we're finding less and less of them in the Earth's crust. Second, pulling them out of the ground from their ores is an incredibly difficult and energy-hungry process. And third, because of that, it is just way cheaper and easier to recycle them than it is to start from scratch every single time.
And this is where we come full circle. The very nature of that sea of electrons doesn't just make metals strong. It also makes them incredibly easy to melt down and reshape without losing their amazing properties. That's the superpower that makes them, for all intents and purposes, infinitely recyclable.
Which leaves us with this one powerful idea to chew on. The properties that make metals useful are the same properties that make them sustainable. Their fundamental atomic secret isn't just about strength or letting electricity flow, it's also the key to a circular, reusable future.